All right, so this video is going to be on conjugation as well as resonance and a lot of information associated with it. So we've done this already, but by definition, conjugation, as a reminder, is when we have p orbitals that overlap on 3 or more adjacent atoms. Okay, so we've seen this before. We saw this, I think, like chapter 1 last year. So we have, in this case, this diene and then this allylic cation right here. So we got 4 p orbitals in a row on the left and then 3 in a row on the right. Okay, so for this diene, there's the 1, 2, 3, and so that's why this guy is called a 1,3 diene. And so 1,3 dienes are really we have specific reactions that we're going to go over in this chapter, so it's important to understand the resonance associated with this and the stability associated with the conjugation. Okay, the allylic carbocation, we also know that it has a particularly unique stability, and that is due to the resonance. Okay, so the idea of a conjugated system is kind of the topic of the next couple chapters, and so we really want to understand this, but conjugated systems are as opposed to like non-conjugated systems, so you can still have a diene but not have it be conjugated. Okay, so the butadiene on the left, there's obviously one resonance structure. We have a positive and negative charge on either end, and then the one on the right, it doesn't have a resonance structure. It's not a conjugated species because you don't have 3 p orbitals in a row. That middle carbon is actually sp3 hybridized, not sp2, and so there's no resonance. Okay, now this right here would be the delocalized electrons when you kind of draw that hybridized or that hybrid resonance structure, and this is kind of the representation of this species as a whole. Okay, and so these delocalized electrons are spread throughout, kind of evening out the charges, whereas the localized electrons on the right, where we have no resonance structure, those are just localized electrons. And so if we had a charge, it sits in one area or on one atom. And so those isolated dienes are not very stable, and then those conjugated dienes are going to be very stable. So again, isolated dienes on the right, conjugated dienes on the left. Okay, now let's take a look at this allylic carbocation. So we have a resonance structure. We already know this stuff, right? We're good with this especially when we talked about substitution reactions, but just real quick as that reminder, right? This is resonance or conjugation, and then it also, we want to make sure that we remember that it provides stability. Okay, and again, that's just because that positive charge isn't on one side or the other. It's kind of distributed throughout that entire molecule, or on the left and the right. So real quick, as just some practice, which are conjugated. Okay, so we've got, I'm going to draw like 5 structures for you. Let's see, 1, 2, 3, let's do that. And then I want you to pause the video and then of course try them on your own and then see what you get. Okay, all right, so go ahead and pause it and then we'll go over the answers, right? So there's a p orbital, there's a p orbital, there's a p orbital. That's 3 in a row already, but turns out we have 6 in a row, so that's definitely a conjugated species, right? So 6 p orbitals in sequence. That's way over the minimum, and so that's more than 3, and that is indeed a conjugated system. Okay, now let's take a look at this next one. So we have a p orbital here and here. We also have 2 over here, but they are not adjacent, right? So we do not have 3 in a row. We only have 2 p orbitals in sequence, and twice though. And so this is actually not a conjugated system. So this would be an isolated diene. Okay, important to distinguish between the two. All right, so we have this p orbital here, 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 and here. That's 4 in a row. This one's kind of tricky just because the orientation of it, and the oxygen's in there, and it's kind of weird. People get confused sometimes. So it's just remember, you have a pi bond. It has to be in a p orbital, right? So it's conjugated. There's three. We were kind of already did the allylic carbocation, but that's three p orbitals in sequence, and so therefore it is a conjugated species. Let's write that here, conjugated. All right, so this last one, there's two right there, and then there's one over here. Are those in sequence? No. No, they are not. There's only two in sequence, and so this is not a conjugated species. So hopefully you got the same answers that I did. If you didn't, let me know. Then I'll walk you through it again. All right, so what we want to go over next is basically resonance and allylic carbocations. Now, I know you know this stuff, but I still watch this portion of it. Don't skip it, because I really, at the end of it, I kind of have a good problem for you that I want you to understand and also be able to answer on your own. Okay, so we've got the resonance structure, the resonance hybrid. You see the delta positive on the left and the right side, right? And so just real quick as a reminder, I want to draw out the stability of carbocations. This is again chapter 7. Chapter 7 doesn't necessarily contain the stability of allylic carbocations, but I myself gave it to you. Okay, so just remember that the allylic carbocation was about the same stability as the secondary carbocation. Okay, so there's our tertiary. So that is on the far left a methyl carbocation, primary, secondary, allylic, and then we have a tertiary carbocation. Okay, so as we go from left to right, obviously we have the increasing stability of the carbocation. Okay, and so again, allylic and secondary are going to be approximately the same. Okay, and of course, at a first glance, that allylic carbocation looks like a primary carbocation, but it's not. It's actually stabilized because of resonance. Okay, so what we want to do for the problem is use resonance theory and Hammond postulate to explain why this allylic halide is more reactive than its saturated counterpart, this chloropropane, in an SN1 reaction. So why is the allylic halide more reactive than the just the alkyl halide? Okay, and just for nomenclature purposes, this is a 3-chloroprop-1-ene, and then we have 1-chloropropane, right? We should know these. And again, resonance theory and Hammond postulate for an SN1 reaction. So you have to think, right? So really, what is an SN1 reaction? Well, we have to think about the rate determining step and what dictates the reactivity of an SN1 substrate. And so let's draw our energy diagram, because we're talking Hammond postulate and whatnot. So the red structure is obviously going to be the chloropropane. And remember, in the first step, the rate determining step of an SN1, we have a formation of a carbocation. Okay. And now if we form a carbocation with this guy, with the chloropropane, it's a primary carbocation. That guy's pissed. But we do know that an allylic carbocation is actually lower in energy. Sorry, my pen is mad at me. Allylic carbocation is lower in energy, so that blue line above is going to represent the final product, the allylic carbocation's energy. Okay, and that's lower in energy because of resonance, right? And HP, the Hammond postulate, states that the product in endo. Hold on. Let me let me fix that real quick. So my wording was going to be weird. So the Hammond postulate states that the transition state in endo reaction resembles the products. Okay, and so what does that mean? That means that the transition state is lower than the the chloropropane's carbocation that form. So the propyl cation. And so that means that if we have a lower transition state for the blue line, which represents the allylic carbocation, then we have a lower activation energy. If it's lower in activation energy, then that means it's a faster reaction. Okay, and of course, it's lower in energy because of resonance. So that's like all of the. It's a SN1 reaction. It was the resonance and Hammond postulate explaining why. Okay, and so you should be able to do that on your own for sure. All right, so let's real quick talk about some common examples of resonance. Again, we already know this stuff, right? So this is easy peasy. 4 general types. We have an allylic type system, which we of course just went over for the carbocation, but we also have the acetate form. Okay, so just being a little redundant here and throwing it at you 27 times. There's the allylic carbocation, the acetate. We know how to draw this from general chemistry, right? This is a piece of cake too. And this is the resonance structure here. You always got to remember to move your charges, right? So don't forget that. But the general type of, so this is an allylic type system, and that means that we have an X doubly bound to a Y, where X and Y are some atoms, and then which is singly bound to a Z, where Z is some atom with a p orbital. And in this p orbital, it has 0 electrons, which would be like the allylic carbocation. It could have 1 electron, which would be like what we ran over recently, which would be a allylic radical. Or we can have 2 electrons in that p orbital, like this acetate ion. Okay. Now remember this because we just said those electrons were in a p orbital, right? So we're gonna kind of go over something in a second that we got to remember that information. So we already knew this, but we just want to point it out again. Okay. So the second type of resonance structures would be conjugated double bonds, right? So benzene ring, we know we've got resonance for days. It just goes in circles, and that's why benzene is particularly stable, which we'll go over very soon. And then this diene right here, right? We have this conjugated system, which we just went over again. We got the positive and negative charge on the right. And then we can draw another resonance structure where the positive and negative charge are switched. And that's the blue structure and the shifting of blue electrons, okay? And that's conjugated double bonds. I mean, there's not much to add about that. But for the third type of resonance structures, we've got ourselves cations having a positive charge that's adjacent to a lone pair. Okay, now we've seen this a couple ways, but the new way would be like on an ether where we have a positive charge adjacent to that oxygen, and that lone pair can donate to create that carbon oxygen double bond. Okay, positive charge on that oxygen, an oxonium. Okay, and number 4, we've got double bonds having one atom more electronegative than the other. Ooh, you know what? Sorry, I just remembered. I wanted to give you another example of the cations having a positive charge adjacent to a lone pair, because it's kind of a refresher for last year's chemistry. Electrophilic addition of HX to an alkyne, right? So if we have this alkyne, we have the addition of HBr, for example, and we have 2 equivalents. We're going to get 2 additions of HBr added to the alkyne, right? But remember, this was selective in adding the bromine to the same carbon, which was the more substituted carbon. Okay, so why was that? Well, that was because we had a carbocation intermediate that was stabilized by the lone pairs of that bromine. Sorry, this drawing sucks. Let me just zoom in real quick and make it better. Choose a different pen. Okay, so we've got a bromine. Got all those lone pairs. Got a positive charge. Can donate into that p orbital to create a Br carbon double bond, which is a bromonium ion, right? And that's just another example of having an atom with lone pairs being adjacent to a positive charge. And that actually made that carbon more stable and allowed that second bromide to come in and attack that carbocation that the bromine was bound to. So that's why we ended up with 2 bromines on the same carbon. Okay, so this particular one, we have a carbonyl group, and the pi bond goes up to the oxygen because the oxygen is more electronegative, right? Leaving that carbon positively charged. So I'm not super in love with this one, but this is in your textbook, and so we're talking about it. But resonance structures are like the best ones are the ones that have an octet for all their atoms, and that carbon doesn't have an octet, so it's not a good resonance structure. But anyway, right? So let's talk about resonance hybrids. So a resonance hybrid is basically like an average of all the resonance structures. Okay, so if we're averaging all the resonance structures, what we're going to do is draw dotted lines to represent the flow of those pi bonds, right? So it's almost like we have a partial bond between every single carbon, in this case for benzene, because we can draw a resonance structure where every one of those carbon-carbon bonds ends up with a double bond. And so the hybrid more closely resembles the best resonance structure, okay? And so that's actually equivalent for the benzene ring, so it doesn't really matter in this case. But remember, the best resonance structure kind of leads to the idea of major contributor versus minor contributor. And so this was a topic brought up in last semester's OChem. Okay, so basically the major contributor is the one that's lower in energy, and the minor contributor is the one that's higher in energy, right? So how can we draw a resonance structure that's lower or higher in energy? Well, we just saw one with the carbonyl group, right? So I think it's, at least with that example already, it's pretty obvious how we might be able to do that, but let's bring up 3 ways to kind of determine the relative energies, okay, of the resonance structures. So that way we can kind of assign the major contributor and the minor contributor, okay? So the first way is what we've seen already, right? Where we had that carbonyl group and the pi bond kind of moved up. So, but first, just in words, the more bonds and fewer charges means that we're going to have something that's lower in energy, okay? And so here's that acetone, right? We shift that pi bond up to the oxygen, creating a positive charge on the carbon and a negative charge on the oxygen, just like above, okay? And the one on the left, it's neutral, so it doesn't have any charges. The one on the right has hella charges for how big it is, right? And then we have on the left, we got octet is fulfilled, and it's overall just a better resonance structure. So the one on the right obviously has charges, and then there's not even an octet on that carbon. Again, pissed, right? So, but that just all comes down to the number of bonds. It has less bonds, okay? Because number 2 is specific to that idea, where the resonance structure where all the atoms have an octet is more stable, okay? So resonance structures where every atom has an octet is a better resonance structure, okay? So, for example, we saw this one already. We have an oxygen, an ether basically, with a cation on the carbon. And here's the resonance structure with the oxonium ion, the positive oxygen. Now that one has an octet on every single atom, and therefore it is better. I mean, think about it too. It also has more bonds, right? So it's kind of following the rule above. This one doesn't have an octet. That oxygen is charged and pissed, just wants to react, but it'll just take the electrons from the oxygen real quick, and then they'll be happy. So that's cool. Something interesting to point out is that the oxygen is more electronegative, right? So it's still a better structure, resonance structure, even though the oxygen is more electronegative and the positive charge is on the more electronegative atom, okay? So that just tells you how important it is to have an octet, okay? Now, resonance structures that place the negative charge on the more electronegative atom are the better ones, okay? So that's kind of related to the above one, or the above statement, I guess, but we're talking about negative charges now, right? So if we have the choice to put a negative charge on a carbon or an oxygen, which one do we want to put it on? We want to move it over to that oxygen, okay? Now, this is or on the right, is the oxygen is more electronegative, and so that's the better resonance structure. And so when we're talking hybrid structures, that would be like the major contributor. And this topic is important because when we're talking about major contributor, then perhaps that could be the way this particular molecule reacts. But maybe not, right? It's just, you should be aware of both scenarios or possibilities, okay? And you should be able to explain them as well. All right, so we have this structure right here, this carbocation. We want to be able to draw all the resonance structures and then also identify or ID the major contributor, okay? Now, go ahead and pause the video, try it on your own. I'm going to go through these pretty quick because it's resonance and we've done this for days. Now let's shift that pi bond over to where that carbocation is. Now we get the carbocation shifting. Now we've got this new carbocation, right? So I'm going to draw in those lone pairs for the oxygen just because they might matter soon. Now the next resonance structure is just moving that pi bond over again. And we got a new carbocation intermediate. Or carbocation compound, whatever. And then the lone pair on the oxygen can actually create a carbon-oxygen double bond. And we get an oxonium. And there you go. That's 1, 2, 3, 4 resonance structures. Don't forget your first compound. That is a resonance structure technically. So you get 4 of them, right? Now, which one's the major contributor? Think about it. It would be number 4. Now, why is it number 4? Well, if we're thinking about the above rules, then that's because the charges are all the same, really. So that's kind of canceling out. We don't have more or less charges. The number of bonds, there's more of them in number 4, so that actually works out pretty nicely. And then, in addition to that, number 4 also has an octet for every single atom. Okay, so we can ignore the idea of number 3, where the negative charge is has to be on the more electronegative atom because we have a positive charge. So it doesn't apply here. And so there you go. That's pretty much it for that example. Now let's move on to electron delocalization, hybridization, and geometry. So this is, again, something we talked about before. We're just bringing it up again, a little refresher. And it's actually in this chapter, even though I brought it up before. Okay, so we have this compound right here where we have a negative charge on the alpha carbon, and that carbonyl, we already know that's sp2 hybridized, right? And this oxygen is also sp2 hybridized. It's got 3 regions of electron density. But what about that carbon? So that carbon has 4 regions of electron density. So does that mean it's sp3? That's the question, right? If I'm asking that question, then it's probably no, right? So here's the thing. Can we draw a resonance structure? Yeah, we can. So follow the blue electrons, right? We create an O minus, and then we create a carbon-carbon double bond, okay? So that carbon now, it's not ambiguous at all. It has 3 regions of electron density, and it is sp2 hybridized, okay? Well, since it's sp2 hybridized there, it always was sp2 hybridized, and so were the other 2, okay? Oxygen on the top is also sp2 hybridized, and the way you can justify it is basically remember that resonance structures are 2 representations of a molecule, and it kind of like the molecule actually looks like an average of them, right? And some weighted percentage, right, with the major contributor or the minor contributor, it doesn't matter. It's still an average of them. And so that means that the p orbitals that are in creating those pi bonds in each of those structures was always there. And so you have to have 3 in a row to have a resonance structure, right? And that's also going to create stability for this particular compound because we're going to put that negative charge on the oxygen, right? So that would actually be the major contributor anyway of the structure on the left. And that's it. That's basically the extent of the discussion on the delocalization, hybridization, and geometry. We just need to remember that if you can actually create a resonance structure, then we have to rethink the hybridization of that particular atom and take a look at it in two separate pictures. Okay, so that carbon is sp2 hybridized, and so are the other two, the carbon and the oxygen adjacent to it. Okay. All right, that's pretty much it for this. So let me know if you have any questions. Bye.